Good morning. Welcome on the lab on neural networks. Today we have a very important subject, as we will continue with better, a little more complicated model of neural networks. During the previous labs, we arrived at the simplest neural network, and this was perceptron, which is just one neural network. Of course, the power of such a computing device is very limited. We can increase the power of single neuron by adding more perceptrons and let them work together. For example, we can combine output of several perceptrons, and this can be used for more complicated computations. Nevertheless, the real power of neural networks comes if we can do much more complicated combinations of neurons, where output of one neuron is connected to inputs of several other neurons. In general, this could be complex graph, but very early it was recognized that when we limit the structure of the graph, we can obtain model which is still powerful and easier to manage. And one of these models is a model of multi-layered perceptron, which is trained using certain learning algorithm, which is called backpropagation. So sometimes you can hear the notion backpropagation network. So let me start with briefly introducing the model. You will see it in the slides. So I will switch to share. I will share my screen with you, and in the slides, you can look for multi-layered neural networks. And in this part, that is described the model we will deal with today, but I will not go into much details. I will just explain how it works, and then we will look at the algorithm for training such a model, and we will try the algorithm, but without reviewing the theoretical derivation of the properties of the model. So the model looks like this. The neurons in the models are organized in layers, and connections are only within two successive layers. So here at the bottom, there is input layer. All neurons from the input layer are just copying their inputs and sending them further into the network. Then here on this scheme, there is one so-called hidden layer and one output layer. So all input neurons are connected to all hidden neurons in the first hidden layer. Then the first hidden layer is connected to the next hidden layer. In this case, we have just single hidden layer. And from the last hidden layer, there are connections to output layer. The neurons in the input layer do not perform any computation, just copy their input. So the input is a vector, which is put on the input neurons, and they send it to the neurons in the first hidden layer. The neurons in the hidden hidden layers and also in the output layer are computing. They are actually perceptrons. Perceptrons but usually with different transfer function or activation function as usual perceptron. We will see it in a while. So the information flow is so that we put input vector and the input neurons. They send it to the hidden layer. Neurons in the hidden layer compute weighted sum of their inputs. Transfer the output using the subtract. They will add the bias and then transform it to using some transfer function, and the output of all these neurons is sent to all neurons in the next layer. And the output of the network is the output on the output layer. Here is a derivation how to adjust weights in such a network when we train the network. I will just go, or maybe better up to show the. If we have such network, then we train it similarly as we train perceptron. So we have some training samples, and for the training samples we know the desired output, and at the output layer we obtain some output, and we can compare all outputs on all training samples with the actual output, and we can compute some error function. The error function used in multi-layered network is usually this one, is the sum of squared differences. So for each pattern, it is indexed by the variable p, we compute the actual output. So this is output on the output layer. So jth neuron of the output layer, output of the neuron for the pth input pattern. From this we subtract the desired value for the output. So this is what we would like to have, this jth output neuron for the pattern p. We squared the difference, and we sum all these differences for all neurons in the output layer and for all patterns, and we multiply it by 1/2. It may look strange that we multiply such an error by 1/2, but when you will go through the derivation for the learning algorithm, you will see that we will compute derivation out of this function, and in the derivation there will be 2 times 1/2, so we obtain just 1, and some derivation of the inside of the error function. So what I would like you to do with you today is to manually perform step of the adaptation algorithm, which is called backpropagation algorithm. And backpropagation, the name is derived from the way how it works. The algorithm first initialize the weights and of the whole network. Then it presents one training pattern in the form input and desired output. This is the training pattern. The network calculates output of the for the input pattern. During the calculations, the transfer function, activation function of the neurons is used sigmoidal transfer function, which is this one. So 1 divided by 1 plus a to the minus lambda xi sub j. Xi sub j is the potential. Potential is it is actually the weighted sum of inputs of the given neuron, and lambda is is the slope of the sigmoid transfer function. So for the we have already seen the lambda in the beginning when we computed some or programmed, implemented some normalization functions. And the backpropagation algorithm works in the following way. It adjusts the weight value for the weights. So, as I said, initially the weights are set random, and then the value for a weight between neuron I and neuron J in time step t plus 1 is the weight of the value of the weight at time step t plus alpha times delta sub j y sub I plus alpha sub m times difference between the weights at time t and weight at time t minus 1. This last term is called momentum. Actually, this is an improvement for the basic backpropagation, where we actually use the previous adaptation step. So the previous difference between the weights it's time step t and time step t minus 1, and we continue the change in the same direction, multiplied by some constant alpha sub m. And for the adaptation, we use the following formulas for computing delta sub j. There is one important thing. This formula is general for the whole network, but you must be aware that I indexes neuron in one layer, and J indexes neurons in one above layer. And for computing delta sub J, we will also need neurons from even higher layer, which is indexed by K here. So the formula for J sub delta sub J is d sub J minus y sub J times lambda times y sub j times 1 minus sub j. This is for output neuron. You may notice that it's indexed by j. When j is for the neuron in the output layer, then this formula is used, the first form. The second form is used deeper in the network. So the backpropagation algorithm works in backwards direction. So it starts at the output layer and computes the delta terms for the output neurons. Then uses this delta term to update all the weights between the last hidden layer and the output layer using this formula. And then it continues computes the delta terms for the last hidden layer, and using the second formula. And this value is then used to update weights leading to the last hidden layer, and we move deeper and deeper into the network until all the weights are updated. So your task, the first task for today, will be to compute just one step of backpropagation. Because even if we know such a formula, we still need to set the learning constants or learning rates, alpha or alpha n, in order to work. But without knowing how much the influences the change of the weight, how much influences the output of the network, we will not have the real idea how many iterations of such algorithm we will need. So similarly as for perceptron, the training set contains several training patterns, and the basic method how to apply the backpropagation algorithm is that we submit the first training pattern, we compute the output of the network, and after that we compute after that we adjust the weights backwards, from going from the output layer till the input layer backwards. We adjust weights in the whole network. Then we take the next training pattern, put it in the input, compute output, and backwards we adjust the weights. And this is repeated for the whole training set. And usually it must be repeated many times also for the whole training set. Similarly as for perceptron, we use these iterations during the training. So let us start with a simple network. So for that, please, maybe I will keep the slides at hand by opening them in a separate tab. Yes, and in the Moodle page, oh, it should be in English. In topic 4, please look into the text, in the first text, multi-layered neural networks and the backpropagation algorithm. So this text describes an exercise in which we will compute output of such a network and then apply the training algorithm, the backpropagation algorithm. As you can see, this was generated from Matlab, so you can directly open it in Matlab when you download this source code. And I would like you to do that now, to open the source code in Matlab. So once again, topic 4, the first item, and at the end there is link to the source. So I will open the file. So once again, working with oh, yes, this is the text. So we will work with some training set, some input patterns and desired outputs. So for the whole this part, and actually for all networks trained in the deep neural toolbox in Matab, we will use the convention that all input vectors are always column vectors. So similarly as we have it for the perceptron. And we will have a simple neural network with topology 2 to 1. This means the network will have 2 input neurons, 2 hidden neurons in one single layer, and 1 output neuron. So let us start with giving the weights, original weights of the network. So we will not generate the network now, the weights for the network now, but we will use some values for the weights. So let the weights between the input and hidden layer, so this is the mnemonics for the identifier, weights between input and hidden layer, it's this matrix. And in order to compute easily, you know from the perceptron that if we have the weights in a row vector and the patterns as a column vector, then we can use so weights column vector and patterns column vector. Weights row vector, patterns column vector, we can multiply them using matrix multiplication. So here always one row of the weight matrix contains weights for the connections called synapses leading to a single neuron. So the weights 1/2 and 1.5, these are weights for the first hidden neuron, the first hidden layer. We have single hidden layer in the model. And the second row are weights for the second hidden neuron. So the first one is the weight between the first input, -1/2, and +1/2 is the weight from the second input neuron. As I said, the network will have one output neuron. So for the output neuron, we have also weights, and these are weights between hidden and output layer. This is the mnemonics for the variable weight between hidden and output layer, and the values for the weights are 2 and -1. The neurons will have also biases, similarly as perceptron, but in contrast to perceptron, now the bias will be added, not subtracted. But if you remember, when we use this extended weight vector and extended input patterns, then the value of the bias was actually added to the potential of the neuron. So this is almost the same. So the values for the biases for the hidden layer are 0 and 1/2, and the bias for the output neuron is -1/2. So altogether, we will build extended weight matrix between the input and hidden layer. So the suffix B means that the biases will be added. I forgot to execute the sections of the code, so this must be executed. something wrong. 22.5. So it's now it works. So I will change the form. Wait from input to hidden. It's already stored. Wait from hidden to output. And biases of the hidden neurons. And bias of the output neuron. And we concatenate the weights between the input and hidden layer and biases of the hidden neurons. We obtain the extended weight vector, so weight matrix. So this is the weight matrix between the input and hidden layer, including the biases. And similarly, we will do that for the weights of the output neuron. So we add the bias as the last weight. So we have it. As I said, the neurons in the multi-layered perceptron usually use some continuous and function, which this is not the signum function used for perceptron. And usual function is the sigmoid function, which is here it is code of the function that of course you can read it either in the PDF description. So it's 1 divided by 1 plus e to the minus x to the power minus x. Actually, what's missing here? In general, here the x is multiplied by a slope, and in this exercise we will use slope lambda equal 1. So, in the slides, in all this formula, the slope lambda will be 1. Okay, let me go back to MATLAB. And we will start with the first task. You should compute the output of the network for the input pattern P1. So it's better to copy the formula for the pattern. So the first pattern is -1, 1, this input, and you should compute output of the network. As for the algorithm, for the backpropagation algorithm, we will need the values for the outputs for all the neurons. We will go through the evaluation, so through the forward path where we put input to the input neurons, and compute output on hidden neurons, and then output on the output layer. So I unintentionally closed the window. So please compute output of all hidden neurons for the pattern P1. So let us denote the output from the hidden layer y_h. And you should compute output of on hidden neuron. So if we compute the potential on the first hidden neuron, so for computing we will need the input pattern P1 and weights between input and hidden layer. So potential C on the hidden layer for the first neuron. It's of course we will need also the bias. This should be. We need not only one but also input to hidden biases. So what is the value? What is the value? Compute please the value of the potential on the first hidden neuron for when we put P1 at the input of the network. Potential is the weighted sum of its input plus bias, of course. Please do that now. Yes?
It's a column vector of 1 and 1.5.
Okay, how you obtain the how you obtain
I
that?
multiplied the weights of input vector to the hidden layer times P1 plus BH.
Aha, so you work with the whole matrix W underscore I underscore HB.
I did this. I sent it to the chat.
To chat. Okay, I will check it.
I'm not sure whether I'm pronouncing the letters correctly.
Yes, I will take it from the chat. So this is copied from the chat. So we know that all rows, so the first row of the matrix W underscore I underscore H are the weights leading to the from the input neuron to the first hidden neuron, first row of this matrix, times P1. Well, this will compute the matrix multiplication. So we obtain the weighted sum of the inputs, and we add the bias. Okay, if you remember, this is correct. If you remember, when we worked with perceptron, we used extended input. And we can also here use the extended input vector together with the matrix containing not only the weights between the input and hidden neurons, but also including the bias. How can we do that? So the goal is to simplify this formula.
We could use. Oh, I'm sorry. We could use the. I'm sorry. We could use the weight with bias, but I didn't figure out how to use it.
So when we use the weight with the bias, then of course the multiplication cannot be done. But we use something, we made something when we computed the output of perceptron. What was that? Excuse me, I will collect my list of students so I can mark points for you.
Maybe we could add a single one to the input input vector, so it would add like a fake neuron with the
we use actually extended input. Similarly as for perceptron, we extend the input vector by new item with value 1. And then, of course, what was? Wrong bracket squares would be there, of course. And in this way, we obtain the output for both, not output, the weight, the potential on both hidden neurons. The output of the neuron is computed by transforming the potential by by the transfer function, and in our case, the transfer function is the sigmoid function. This one. So this function, we can implement this function in MATLAB, but actually in the deep learning toolbox, which is also already accessible in MATLAB, we can use a function logseq. This one. So logseq. Maybe I will plot the function. So for x between -4 with 1/10 and +4. I will plot x again. So we can see that the sigmoidal transfer function starts in -infinity at value close 0, and then around 0 it switches the output from 1 in a continuous way to value close from 0 to 1, close to 1. So we can just apply the logseq on the potential. Weight from input to hidden with biases times the extended input pattern. And this is the output on the hidden layer. Okay, so these are outputs on the hidden layer. We will need it for the backpropagation. So I will store the value in some variable y_h output on a hidden layer. Okay, so now please compute the value of the output of the whole network for the input pattern P1. I will note point for colleague Hayek.
I'm sorry, can you repeat?
That's because you helped me. I mean, colleague Hayek. I note 1 point for you.
Thank you.
So please compute with this for all. Compute the output of the whole network. So output for the whole network will be output on the single output neuron. So I would like to obtain some formula y_o equal and something which will compute the output on the output neuron.
So it's gonna be very similar to the previous one, except BU.
Yes, yes. I would like someone else to help me. For example, colleague Babushik, could you help us? How to compute the output on the output neuron? Or someone else?
Well, as colleague said, it's very similar.
Yes.
It's just the weights of the other layer times output of the previous layer. I will put
so from weights from hidden to output with bias times
YH extended by 1.
Extended, so YH extended by 1. This is all?
And it's in sigmoid. No, it's
yes, it must be transformed using log_sig function. And this is the output of the neuron of the network for the pattern P1. Okay, so this was colleague Richtera who helped us. So we can we will not need that, but we can easily compute output of the whole network as in single expression. Sig of hidden output with bias times extended output on the hidden neurons, and this is computed by log_sig from input to hidden with bias times pattern extended with 1. Should be extended with 1. And this is the output of the whole network. Mathematically, we can see that the result is obtained using some function which uses some values for the weights. and values for the input. All the functions used for computing the output are mathematically nice, I mean smooth and derivable. And this is actually the main idea of the backpropagation algorithm, because we are able to compute derivative of the error function with respect to each weight. And the backpropagation algorithm is just gradient descent algorithm. It changes the weights in the opposite direction, opposite to the derivative, partial derivative of the error function with respect to a given weight. So let us compute the error function. For computing error function, we must know the desired output. So if you look further in the text, and I mean in the task 2 here, you should apply the backpropagation learning algorithm for the first pattern with P1, when the desired output is 0.9 and the actual output is 0.5361. So what is the value for the error function? So please compute the error for this pattern when we know that the desired output is 9/10. So please compute the value, and if you know the answer, raise your hand, please. So the value for the error function. The error function is on the slides. Here it is on slide 6. Now we have just single pattern, so this sum will sum only for single value for P, just for one single pattern, input pattern. So we would like to know the value for the error function. It's important to compute it because later we will use some functions from the toolbox of Matlab to compute, to model the neural networks, such neural networks, and it will also compute the value for the error function. That we must know whether error 1/10 is big or small. So I see that colleague Richter knows the answer. I will wait for more people. Please compute the value for the error function for this single input pattern P1. Okay, second student knows the answer. 3, 4. So please, colleague Shubham, can you show us how to compute the error? You can share your screen with us, or you can just write the answer. Oh, you wrote the answer in the chat. Okay, so everybody can see it in the chat. I will copy the expression from the chat. So is this computation correct? Colleague Genchi, is this the same value as you obtained?
Yeah, it's the same.
It's the same. Okay, so this is 1/2, and the squared difference between the real output and the desired output. Okay, so this is the value. Is this error small with respect to the desired output? What do you think?
It doesn't seem to be that big.
But as we can see here, the output of the sigmoid is between 0 and 1.
Yeah.
So the real output for the pattern was around 1.5, and the desired output should be close to 1 or 0.9.
Yeah.
So the difference is quite big. So if some library will report for us mean square error, no, this is the mean square error. Mean square error if we compute average of this square difference, and if we have only one pattern, so the average will be the same. So if the mean square error is such small, 600, it's too big. So the difference is very big. So we need, we would like to have a much smaller difference between the output and the desired output. So the backpropagation algorithm should adjust the weights of the network in order to move the real output. This was computed as output on the output neuron, to move it closer to the desired output. So now we will recompute the adjustments done by the backpropagation algorithm. So we know the value for the error, and after we finish the adjustment, we will recompute the output of the network, and we will compare the errors, and we will see how much it will improve by performing one step of the backpropagation algorithm. So okay, so for the backpropagation algorithm, this is the general formula. The weight time step t plus 1 is the weight of time step t plus some value which is minus partial derivative of the error function with respect to the given weight. As I said, I will not go in the detail for deriving the formula, but for what we need to compute this general formula. We will not regard this term with momentum, so alpha sub m is 0 for us, and we will just look at the first two terms. So this is the original weight and alpha times delta j times yi. So this is the summary. Let us use this slide number 13. So for the output neuron, we have just one output neuron in our network. We need to compute the delta term. Because the neuron is in the output layer, so this is an output neuron, we should use this first formula. Please compute delta on the output neuron. So I would like you to compute something like delta underscore O. There should be some expression which computes the delta term on the output neuron. Once again, for the formula, this is weight between neuron I and J. In our case, J is the 1 because we have just one neuron in the output layer, and and I will index the neurons in the hidden layer. But for computing that, we will need delta J, and J index is indexed in the output layer. We have just one neuron in the output layer, and for that we need to compute the delta term using this first formula. Okay, five students already know the answer. Yes, colleague Shubham already submitted the value. So, Surma, okay. Maybe colleague Genchi, can you show us or say how to compute delta O?
I posted it in the chat, so.
Yes. So I will copy it from the chat. Is this correct value for the delta O?
Well, I think that it is.
Yes.
If you show the slides, we can go through it, I think.
Maybe I can try to put it in a separate window. To put the formula next to the so the desired output minus actual output, desired output. Yes. So in general, this would be D. Desired minus the real output times the real output times 1 minus the real output. This is the formula. Okay. So we know the value of the delta term. It's sometimes called the error term, and the error backpropagates through the network. So now we can compute new values for the weights between the hidden and output layer. So I would like you to compute weights between the hidden and output layer with bias, of course, and I will add suffix 1 after one step of backpropagation. For that we need a formula. Yes, there was a question in chat. You may notice that in the formula there is lambda, but in our case we have lambda equal 1, so it's not included in the expression as it's equals 1. So how to compute the weights from hidden to output layer after applying this formula? So without the term with alpha sub n, we don't regard momentum for now. As you see, the formula is very natural. We take the value for the weight and we add some learning rate alpha times delta J. Delta J is the error at the neuron J. The weights leads to the neuron J. So error there, multiplied by the value which is transferred through the weight, because the weight is from neuron indexed by I. So this is multiplied by output of the neuron, yi. Friedrich Dirac with the answer. Okay. Anybody else? How to compute the new weight between the hidden and output layer? Vinayak, excellent. I would like to see more people to valid. Yes, 3.
Can I have a question?
Yes.
What should we use as the learning rate? What number?
Aha, the learning rate is written in the assignment. The learning rate alpha should be 0.2.
Right, thanks.
I will store the value for alpha. Only two colleagues know the answer, how to compute the new weights. So maybe let us compute just the new weight between the first hidden neuron and the first output neuron. So for the value of the weight between the first hidden neuron and output neuron, the value for the weight is 2. And it should be adjusted using this formula. So to the original value for the weight 2, we should add alpha times delta term on the output neuron times the value which is propagated from the neuron from the first hidden neuron. So see the value output of the first hidden neuron, we see that it is this one, 0.7311. So the new weight, original weight is 2 plus alpha times delta on the output neuron, delta on, times the output on the first hidden neuron, and this is actually Y01. This is the value. But I would like to have a formula which computes the new weights from hidden to output layer with biases. One in one expression. What's the problem? Why you don't understand? Can you help me?
We have the extra neuron for the bias, so we should use 1 as the output of that. Like we need to update 3 weights, and we had only 2 outputs in the hidden layer.
Yes, you are right. You are right. But you have noticed that when we compute the output on the output neuron, we also use the output on the hidden layer extended by 1. This is very often modeled in a way that we say we have some additional virtual neuron in each of the layers except the output layer, and the neuron has output 1. This one was actually used for computing the output. So when we computed output of the neuron on the output neuron, we extended the output on the hidden layer by 1. This one is actually output of the virtual neuron, and the weight from the virtual neuron to the output layer are modeled in the last column of the extended weight matrix. So in our case, the weight matrix between the hidden and output layer is just one row, and the last element minus 1/2. This models the weight from this virtual neuron, which has output 1.
Okay, and one more.
So this should be used, of course, for computing the new weights, all new weights between the hidden and the output layer.
Yeah, and when you wrote the code to update the value 2, the first value, you wrote y sub o in the last term. Shouldn't there be y sub h?
Ah, I was wrong. You are right completely. So this was wrong. This should be the value which goes through the weight, and this should be I sub h. Thank you, thank you for pointing by my error. This is the correct weight. I'm sorry, but thank you for pointing to the error. So once again, please develop a formula expression which computes new weights between the hidden and output layer after updating according to the backpropagation algorithm. Please raise your hand if you have such formula. So maybe I ask colleague Tepfer, can you put the formula into the chat so we can check it and try it? Yes, thank you. I will copy it. So these are the original weights plus learning rate alpha times delta O times values which are obtained from the hidden neurons, and also the virtual hidden neuron. This is the one. And in order to obtain 3 values for the 3 weights, here we actually need to transpose the output of the hidden layer. Excellent. So I hope all other people obtain the same. I know the point for colleague Tepfer. So we know the new values for the weights, and now we continue backwards. This is the name for the backpropagation algorithm. And now we should compute the delta terms on hidden neurons. So from this formula, we need the second form to compute the delta terms on hidden neurons. Be aware, in this formula, J will index neurons in the hidden layer, and K will index neuron in the output layer. In our case, we have just one neuron in the output layer, so this sum will be just one term, one multiplication for single delta term.
Can I ask, do I understand correctly that the delta value is the same for an entire layer, no matter how many neurons are there?
No. The delta value is different for different neurons. This is the index J. Delta is different for different neurons. So, but thank you for the question anyway. Let us compute it manually for one hidden neuron. In order to have it not just for the first one, let us compute it for the second hidden neuron. So for the second hidden neuron, delta sub 2 should compute this formula. We are speaking about the second hidden neuron. Maybe you are wondering, in general, the formulas here for the weights should include also the information between which layers the weight is computed, where it is located inside the network. In order not to have so complicated formulas, the formula is usually, and in the literature you will see it else everywhere, it's written in such a way that it's assumed that I indexes neuron in one layer and J in the next layer. Similarly here, for computing delta J, we compute delta term on the hidden layer. And for that, we need also weights which lead from the neuron indexed by J to some neuron indexed by K. Of course, K is indexed in the next layer. In our case, this will be in the output layer. So this first part, I mean the sum in the formula, will be just one term. I will intentionally put it in parentheses, and there should be delta K. What is the delta K in our case? Is it in K?
Delta for output?
Yes, it does. Just single one. So there should be delta O times the weight between the J's and K. So, as I said, let us compute for the second hidden neuron. So what is the weight from the second hidden neuron to the output neuron? So here I must multiply the value of weight from hidden to output with which one? We have here I will just here it is. The weight from hidden to output with bias. So these are the weights from all hidden neurons. What is the weight from the second hidden neuron to the output neuron? It's of course this one, -1. So in the formula, here should be second weight. This is not the general form. So now we have the first part. We should multiply it by lambda. Lambda is 1 in our case. And then this term, y sub j times 1 minus sub j. Actually, this part is the derivative of the output. Yes, it's a derivative of the error function with respect. No, this is a derivative of the sigmoid function when the output is y sub j. So output hidden neuron and second hidden neuron times 1 minus output from the second hidden neuron. You know that y sub h is a column vector, so maybe it would be better to write it in this way, that in MATLAB, if it is vector, we can use just single index. So this is what I obtained. It is a delta term of the second neuron that I would like to have a compute delta underscore h, delta terms for all hidden neurons. So the right-hand part of the formula is output of the neuron times 1 minus output of the neuron. Lambda is 1 in our case. So this should be easy. Just we can compute the output on the hidden layer times 1 minus layer. Lambda is 1. I can write it. Here should come something which will compute this first part, the sum. Nobody knows how to compute that. It should be easy. Delta K is delta on the output layer multiplied by the weight from a hidden layer and summed, and the sum is over all neurons in the output layer. In output layer we have now just one neuron. So if we do not put it in general form, then here it should be delta O times the weight from output and bias. Is this all incorrect? It doesn't work. What's wrong with the expression?
We should use element-wise multiplication.
Element-wise, and where?
At the YH, and the 1 minus YH.
So you mean here?
Yes.
Still
No, even in YH.
So you mean here?
Yes.
It's strange. We should obtain delta terms for each hidden neuron. So we should obtain if we have 2 hidden neurons, we should obtain 2 deltas. Or we can also compute the delta term for the virtual neuron, which models the bias, but not 6 values. So 6 values is too much. So what is wrong? So let us work through that. So of course, this part, put it into parentheses, this must be computed element-wise, because according to the formula, we must multiply output of the neuron times 1 minus output of the neuron. So this is really required. Maybe we can just think a little. If we have more neurons in the output layer, delta O will be row vector or a column vector. You may notice that the weight vector is for each neuron we have one row of the matrix. So different neurons have different rows. So delta O will be also better to have it as a column vector. So if we would like to obtain the delta O in form of column, so if I take the last part, these are the right-hand side, right part of the formulas for each delta, and we should multiply it with this term. In our case, delta O is just one value, and we should obtain something which could be used to compute these terms. So for each j, we should backpropagate the error terms from the above layer to the given jth neuron. So for that, we of course need to multiply delta O by the weight for hidden output. So we have three elements here, because in the weight matrix we have also the bias. So this will be the left part of the formula for delta sub j, and from the right part we should obtain all those three values. Here we obtain only two. How can we obtain three? The last value here was for the weight which models the bias. So we should include also the output of the virtual neuron to the y sub h. And here we should compute the output on the hidden layer, extended by 1. Hidden layer extended by 1. We know that we must use the element-wise multiplication, but of course here the left-hand side part, left part and the right part, this should be done for given j. We must take the part of the vector we obtain here, the same element from the vector obtained here. So this should be also element-wise. But the answer is wrong. We should obtain just 3 values, not 9 values. What is wrong with the expression?
After WHOB, there is no element-wise multiplication to the y times 1 minus y.
You mean
Yes.
this should be removed?
Yeah.
But then we obtain single value. This is wrong. We need deltas for all hidden neurons. This is not correct.
Transpose.
Transpose. What should be transposed? If we transpose, excuse me. So if we add transposition here, not correct. So as I said, between the left and right part, only corresponding elements must be multiplied. And now we have the delta terms. So above we computed the delta term for the second hidden neuron. It was this value. And we can see that it's really the second one. So now we obtain the delta O as a row vector. We can keep it in this way. And using delta O, we can update the weights between the input and hidden layer. Because the time for the lab is over, I would like you to do it at home and before the next lab, because such computation of the backpropagation algorithm will be included in the third assignment. So please do that till the next week, so that you can check your computation during the next lab, and then you will use it in the assignment 3. Any questions now? So you should compute also the new weights between the input and hidden layer and recompute the output of the network, and you will see the difference between the output of the network, original network, and the network after one step of backpropagation algorithm. And it is important to know whether this change is big or small, or if we can estimate the number of iterations, how many times we should repeat the backpropagation algorithm in order to move the output closer to the desired output. So if there are no questions, thank you for your attention, and please try the algorithm before the next lab. See you in 1 week. Bye.